Welcome back to the International Consortium of Advanced Technologies and Security beginning curriculum course for Thermography Level 1 certification. This course is an introduction to thermodynamics. This is Module 3. So how does all of this apply to the thermographer? How do you use this information in your work as a thermographer and in the field? It is useful to understand what we are seeing and how we're seeing it, why we're seeing it, because by the time the device or the mass that we are looking at has sufficient energy to, say, glow red, that is, into our visible range, it is usually too late to do anything about it. Now, while that is not always true, it is 99% of the time. It wasn't true, for instance, on the USS Kitty Hawk in 1991 when we found an aircraft elevator which they wanted us to examine, and when they just turned the power on the elevator as we were cooling off the dewar on the large camera that we had at the time, pouring liquid nitrogen into the dewar. Dewar is the holder of the liquid nitrogen, and warming up the large computer that was worn on the chest. It was a very large device, Thermal Vision 570 or 580, I believe. We could see the contact was starting to glow red. Now, in that case, very little needed to be done. The device literally needed a large nut and bolt loosened and sandpaper put inside, cleaned off, blown off, and then reassembled. But usually, but that's a very, very large contactor. The contactor itself probably weighed several hundred pounds. That was a very large elevator. Of course, it's lifting aircraft onto the flight deck from the hangar bay, so that's a very large device. Most devices you see will not be that large, and so we want to catch it well before it gets to that range. In thermography, we're looking at the spectrum of light outside the visible range. The camera separates these energies and assigns artificial colors to those spectral ranges and energies given off so that humans can see those differences. So the thermogram is an artificial representation of the thermal energy given off by the subject that we see in the viewfinder of the thermal imaging device. This NASA illustration illustrates the various wavelengths of visible light and others that shows pretty much a good piece of the electromagnetic spectrum. And showing it, NASA uses infrared for spectroscopy, which is compiling different ranges of light together to study objects from space, so it can tell specific kinds of subjects by the frequencies of light it gives off. Not just one frequency or a narrow range, but all of the light range. That's what spectroscopy is. The light range, the light ranges of infrared are generally considered to be 0.76 to 0.9 nanometers. A nanometer, expressed usually as a mu, is a nanometer is a billionth of a meter. So it's less than a billionth of a meter long. That is, a wavelength is measured from the peak of one wave to the peak of the other wave. That is a wavelength. So again, the near infrared is 0.76 billionths of a meter to 0.9 billionths of a meter long. A little above that, or that and up, is from 0.91 billionths of a meter or nanometers to about 2.35 nanometers is the mid-infrared range. The range we're concerned with is 10.4 to 12.5 nanometers. That's called the thermal range, the thermal infrared area. That's given off sheerly as heat. It doesn't just absorb, it actually warms things up when it goes into them. Okay, so remember, the hotter something becomes, the shorter the wavelength of light that it emits. So the infrared device does not need to see the entire infrared range. It's a scientific instrument that performs its job very well, enabling visualization of the heat normally outside the visible range or visual range of humans. The visual range is the colors that you see there that are visible to the human eye, of course. Infrared is not. In thermography, we apply thermographic principles when we examine a device. And many of those are built into the device itself. Many we used to do by longhand, by very long equations, are now done internally by the device or by the software you use for analysis. However, you must be aware of the reasons you are seeing these phenomena and look through why and how the heat is reaching you to figure out what the problem itself is. In thermodynamics, we think about the quantities which describe the system we are looking at. The volume of temperature, the pressure of the gas, tell us something about the system and the work it can do. If you're an engineer and working on a machine that you're trying to do, these are very important. If you're trying to analyze what's wrong with the device, you still need to understand those. Electromechanical systems do work and therefore have waste heat, which is not an issue normally, except it may be, like as before, an environmental issue. You may be heating up the environment that it's in, or it may be a problem with the efficiency of the engine. Or you may have a fault, something that's going wrong with the machine, and that's where we come in. In thermal imaging, we're dealing with what is hot, why it's hot, where the energy is coming from, how did it get to our imaging device. Is it a simple image? Is it a complex image? Is the device simple? Is the device complex? We must differentiate between the heat that is normal and the heat that is the indicator of a problem, as it was in this image. This image is a motor which is off to your left, an electromechanical device that is driving a different device. This is probably driving a fan. I forget at the time, I'm sorry, but it's probably driving a fan. But intermediate to that, between them, is just simply a bearing that's holding the pulley, because the belts pull a lot of pressure on it. You don't want that pressure on the pulley. You don't want the pressure on the motor. You want the pressure on something intermediate to that. And here we do see a problem. You'll notice in the thermogram aspect of that, it's the right side is a little bit hotter than the left side. So this is probably a misaligned pulley that is pulling angularly on this bearing and causing it to overheat. So we need to understand what's causing the heat, why it's causing the heat, and according to the specifics of that device, how do we repair that? What do you need to do to stop this problem? The problem is, of course, that the lubricant inside here has a specific range of heat it can operate in. Then it starts slowly breaking down, or it increases the breakdown. It slowly breaks down anyway. Any kind of a carbon atom will break down over time. Okay, but in this case, you have a lubricant in here. The lubricant is added, it's maintained, it's changed once in a while, but it's becoming hot, so it starts breaking down faster the warmer it is. And if it gets to a critical point, that will break down, causing this to seize up and this device to stop working. We need to remember and to ask in every case, what is it we are seeing? Why are we seeing it? Why are we seeing that heat generated? And what path did it take to get to us? What caused this condition, or is the likely cause of the condition? And is this normal or abnormal? Every abnormal heat condition is a problem. Remember, heat is thermal energy transferred from a region of high temperature to a region of lower temperature. Remember the zeroth law, the second law also? Okay, it's flowing down the thermodynamic gradient. It's always seeking to obtain thermal equilibrium. Okay, in this case, you don't want it to. You don't want your whole space this hot. You want to find this problem, identify it, fix it before that problem becomes an issue, because it will become a fire long before it equalizes the heat in this space. Okay. Heat is thermal energy in transit. Heat is easily detected using a thermal imaging device. Here we have a problem that is merely 11 degrees over ambient, so it's an intermediate problem. But what caused this? And in this case, the hottest spot is where that that little plus sign, if you can see it, to the left side, but not at the end of the blue line, is the actual problem area itself. It's the problem of highest heat that we can see because, again, where the connector itself is a little more complicated. So when it wicks to that particular point, we can see the heat is the connection itself. It needs to be probably taken apart and cleaned and tightened. At times you can just tighten these and the problem will go away. Now remember this, we are not looking at the temperature. We are looking at the heat being radiated. It is the apparent heat, not directly the temperature. The heat can be seen in the thermal imaging device, and we can measure that heat by the device because we understand the formulas of how it's being given off. But you need to understand the conductivity. You need to understand the emissivity. If you have your emissivity off, you could be considerably off in the temperature that you indicate is, and that is of course the rating of the problem. The seriousness of the problem is determined by that. So it is the apparent temperature, not the actual temperature that you're looking at. So when you're viewing it through a thermal imaging device, realize it's the kinetic energy transferred by conduction to the surface and then radiated out to the imager. We will express that as a temperature, but it's the apparent temperature. You're actually seeing the energy given off as radiation. Let's review again the three methods of heat transfer. The first is conduction, the transfer of heat between two parts of a stationary system caused by a temperature difference between the parts. Okay, again, zeroth law, second law. It's going to flow down a thermodynamic gradient from one to another until it gets to equilibrium, if it does. Okay, it is the transmission through a conductor. It's the thermal conductivity is the ability of a substance, a mass, to transmit heat, to pass that heat from one part of that system to another, which depends on the atomic structure, the molecular structure of the mass itself, the physical state the mass is in. Is it, if we're talking here about conduction, you're talking about a solid, mostly. Sometimes you're talking about a fluid, such as water, which is pretty dense. So it conducts and it convects. At the surface it radiates. Okay? But conduction is when you're passing vibrational energy from one molecule to another. That's what it is. Convection does the same, but it does it through air. And in convection, the transfer of heat by circulation, the heat moves up because the hot particles move up because they're farther away from each other. They become less dense and more energetic. The liquid or gas, the colder molecules move down in the system. Okay? If you're in your house and it's warm, you turn off your house fans, you will note there's a temperature difference between the floor area and the air in the upper area, especially if you have a vaulted ceiling. You're going to notice the difference in those. Okay? That is convection. That is the cloud that we saw much earlier in the series. We saw a cloud that was convecting upward, where the moisture in the air was that was warm was convecting up thousands of feet into the air and convecting down as it cooled off, lost that energy and cooled off. Now it's very complicated. It's not that simple. Every molecule bumps into another one. It can go up and down at any given second. But that in general, that's what happens. It happens reliably enough to generate that cloud and have it rise high. It's reliable enough that we can make a convection oven, push that heat around and heat up your food more quickly. That's convection. Okay, the molecules bump into each other, speeding one up and the other down. Again, now we're back into Boyle's law. Okay. Radiation is the third method of heat transfer. Radiation is the process in which energy is emitted as particles. Thermal energy is transferred through a medium to a different object by absorption of that electromagnetic radiation given off by one. So one object will emit infrared, the other one will absorb it. This is what you feel when you put your hand in front of a heater and you can feel the heat. The heat is being given off as thermal radiation. Often in this case it's hot enough to get into the actual red range, sometimes hotter than that, but that's radiating out. It's radiation that's hitting your hand. Your hand molecules are being excited, they're moving faster. Your nerves say this is warm. Okay, so that's radiation, convection, and conduction. But there's more to it than that, isn't there? Because when it conducts to the surface, now you have to deal with emissivity. Emissivity is, of course, that ratio expressed as a dimensionless number that compared to a theoretic black hole that tells you how much of that energy is reflected internally or externally, and how much is emitted as radiation. Now, the opposite of that is absorbency. Absorbency is the rate at which electromagnetic radiation strikes a surface and then is absorbed is reflected back in the direction it came from. Actually, it's angle of incidence versus angle of reflection. So if let's say light strikes a mirror at 30 degrees, it will leave in the opposite direction at 30 degrees. So angle of incidence, is equal to the angle of reflection. Okay. But that brings an interesting aspect, and that's the last point on this slide, is that emissivity changes by temperature, wavelength, shape, and surface conditions. Wavelengths is what we're talking about here with a mirror. Well, I can radiate a mirror, and most of that heat will be absorbed by the mirror itself, that is moved through that shiny surface on it's called silvering. That's you use silver or different metals to pass through into the mass of the mirror. Almost all of the visible light is reflected off. So there's a difference in how a given mass handles each wavelength of light. Now here we're only talking about infrared, so it's all going to be handled pretty much the same. We can depend on those emissivity charts to tell us how much is being given off. But this also explains how, if you're looking at an electric contact, let's say there's three of them, you're looking at a three-phase system. There's phase 1, 2, and 3, or if you're under the UK system, or which is what they use in the Orient, it will be phases A, B, and C, actually lined up on a device in the opposite direction. So left to right would be CBA instead of the American system, 1, 2, and 3. And each of those has a marker on it that is, let's say, black, red, and white. Then that device, that insulation, might look a little bit different in each case. You have to understand they might have a different emissivity according to the materials that are used to mark the device. Just as that black plastic insulation is going to be different from the shiny metal contact that you're looking at. So again, in thermograms, sometimes it looks like the insulation itself is the hottest spot when it may be the difference in emissivity. If you have a brand new shiny, let's say aluminum contactor that's put on, but it's put on improperly, it's loose, it's going to start radiating heat. More of that heat's going to be given through that insulation, even though it's a poor conductor. Sometimes more can be given through that insulation than the contactor itself, until it gets hotter and starts to oxidize. So you need to understand emissivity and how it applies to each small piece of the picture that you're looking at, because it can change from piece to piece, condition to condition. The desalination device that I showed in an earlier presentation, it was made of 316L stainless steel, which has a low emissivity. So we had put a spiral scratching on the device to make a pattern out of it, make it look nice, a swirl design on it, and all this. That increased the emissivity that it gave off. But in order to do our testing with a thermal imaging device and with a thermometry, that is a thermal temperature device, we had to know exactly what we're shooting, so we painted black enamel paint on it so we knew exactly what the emissivity was. Otherwise, when you're dealing with large amounts of energy, those numbers would have been significantly off. And here's what we mean. You'll notice that the black enamel paint has an emissivity of 0.8. It's about in the middle of this chart. You've seen this chart before. It's important to not to memorize all of it, but to understand the concept, but to know those things that you're looking at. So that's why we painted that device, which you'll see in a minute again. You'll see me reflecting off of it. Why we painted black spots with enamel paint. We knew exactly what the emissivity was, could make our measurements and metrics of how much energy was being used accurately because of that. Okay. But look again, what happens with highly polished aluminum with an emissivity of 0.139, or about 4% of the energy that hits the surface actually leaves. The rest of it stays inside. If you are reaching out towards a device to see if it's warm and it's made of something like a shiny metal, specifically a silver colored metal, that's why they use silver coloring on the back of a mirror. If it's a silver colored metal, most of the energy is reflecting back inside the device. It's not being given off as emitted radiation. So as you approach your hand and put it up to the device to see if it's warm or not, it might not feel warm until you contact it and you become the conductor. And then it's going to give off 98% or so of the energy into your hand. It's going to get very hot very quickly if it is in fact hot. But you'll notice the temperature difference even if it looks cold to you. If it looks like it's maybe in the 50 degree Fahrenheit range, and it's actually 90 or 100 degrees, your fingers will tell you much more accurately. That's why often in the kitchen, pay attention to what you do. Often you put your hand towards something to see how much heat is radiated. There's still that quality of heat that you can measure. You can't measure the quantity, and then you'll touch it quickly just in case it's too hot, so you don't transfer much heat into your finger and see if it's hot. Then you'll touch it a little bit longer and a little bit longer and a little bit longer until you find out how hot that was. Okay. The imaging device is like that. Now look at the copper. When polished, again, it has an emissivity of 0.023, very much like the aluminum, but when oxidized, it jumps to nearly 8. That's quite a temperature range. Okay, so it will emit much more light, 80% of the light. That should be, of course, 0.80. 80% of the energy that hits its surface when it's oxidized will leave its surface. Now that's good for heat transfer. It helps you get rid of that heat, but it also tells you, of course, that's oxidized. It's heating up the devices around it. There's a problem that needs to be fixed. Many conductor devices that you will see are made of these metals, and herein lies the issue. Now remember this. Let's talk about black body radiation, or something that has an emissivity of 1. Now, there's nothing that has that. You can approximate that, but you can't actually produce it. There's nothing in the universe that's known to have an emissivity of 1. It's a theory. But it's close enough that black body is defined as a body that absorbs all the radiation that falls on its surface. That is, nothing is reflected. Well, look at me. You can see me because some of the light that's hitting me, mostly the visible range, is reflecting off. It's coming from the light source, hitting me and reflecting off, and then you can see my image. That's what happens in regular photography. That's what happens with your eyes normally. If it didn't reflect the light, you couldn't see it. That's the problem when there isn't light. No light is making it from the object to you. That's the benefit of night vision goggles, or thermography, because in night vision goggles, what little light is there is amplified, multiplied by the device itself through phosphorus, and that light makes an image that you can see. In infrared, you're actually seeing the radiation given off by the body, not the reflection of the body. But again, actual black bodies don't exist in nature. It's approximated by a hole in a box that's filled with highly absorptive material, so that a lot of the reflections that would normally get to you are absorbed at various angles. And so that's how you approximate a black body, getting very close to 1, but even that fails. This was fully described by Max Planck, the physicist, a long time ago, and in defining what a black body would be, or what it would be like. how it would behave. A black body is a hypothetical body, again, that completely absorbs all the wavelengths of the radiation incident to it. That is, that come into its body, it's all absorbed again. That's a black body. Remember, radiation is the electromagnetic emission that comes off of something at its surface. And if we double the temperature in Celsius, we get 16 times the radiation from that surface. If we triple the temperature, we see 81 times the amount of radiation. Now you start to see how a thermal imaging device can assign different colors to the different radiation coming off of let's say, a single wire or device. Why there is a gradient, why a wire will wick down to the hottest point. We saw earlier a wire that was wicking away from the contact point, an indicator of it's actually pointing to where the heat is coming from. In the image at the bottom right, tell me why I look hotter than the 99 degrees Celsius metal that's around me in the photo. To know that, you need to know that's stainless steel, so it has a relatively low emissivity. Some of the variations in the heat that you can see are due to the pattern that was scratched into its surface to give it a pattern. Some is due to the heat flows that are on the inside and the way the heat is flowing through the mass itself. So, but why do I look so much hotter? Well, there are, of course, two issues. The first being the low emissivity of the stainless steel device. And then conversely, its reflectivity, the very reason my image is reflected at all. Lastly, you have the additive effect, where my reflection, as you are seeing in that reflected area, you are seeing both that energy emitted by the device and the energy reflected as my heat pattern. And there's more reflected than there is emitted even at that higher temperature. That's why we get a thermal reflection. That's why when you go into the field, you'll be taught, when you see a hot spot, to dodge back and forth, to change the incident of reflection so that you can tell if that heat looks like it's moving, it's a reflected heat. Of course, if in this photograph I had moved to the left or right, the image would have moved with me because it was reflected. If somebody had, would have been very difficult, but if somebody had changed the device itself, it's funny because it's so large, but changed the position of the device itself, changed the angle, the reflection wouldn't have been there because it would have been reflected off in a different direction. Here I had to be perpendicular to that to have the reflection taken. Well, let's read part of that ISO standard, a cautionary note in this case. In most machine cases, it says, the lubricant will have the lowest temperature specification. The maximum allowable temperature should be stated as the temperature above which an unacceptable loss of component life will be experienced due to a loss of lubricant characteristics. Such reductions in characteristics may be immediate, that is viscosity, or long-term, additive depletion of the lubricant. Such criteria will tend to be design rather than material-based. This will require application to specific temperature criteria despite the possible use of common lubricants. Now remember, the ISO standards are very well thought out. Each is present for a reason. Let's examine the motor one more time in light of these standards. This is, again, the picture-in-picture of that one motor that we keep using because it's such a good illustration. The standard takes into consideration what is going to fail and why. In this case, the progression will be failure of the lubricant, then rapid failure of the bearings. It may be minutes, it may be seconds, it may be hours. It's according to how fast it's running, how much heat has been built up, which would be followed by the motor ceasing, machinery failure. But the electrical power continues until one of its components fails. But which one's going to fail? Will the breaker trip? Well, let's hope so. However, when a motor fails mechanically, it can actually experience materials failures. That is, the outer casing could break apart. Or other things can go wrong with it. Any kind of material failure. The materials that make up the motor itself can fail, breaking apart, sometimes explosively. And then you have flying metal in this space, potentially damaging people or other systems. Remember the last flight of the SST, where the flying part of the tire, which had failed, ripped through the wing, killed the hydraulics, caused the critical failure of the flight, and immediately all SSTs were permanently grounded. No more flights of the SST. In this case, very hot lubricating oil and sparks from electricity and potential fire could be the result of the equipment failure. This is why regular thermographic inspections are so critical to the life of machinery, to electric systems, and all those systems which are dependent on them. Lastly, what types of things can be understood better using infrared thermography? Well, nearly everything, from animals to cars, from desalination devices to electronics, from machines to electrical connections. You need to understand what you are looking at, how the heat got to the imaging device, and what that image means. You have to analyze that to see what is going on. From here, refer to the curriculum listing for the remainder of the classwork and the reading assignments and the reports and the testing requirements, and good luck. Remembering that luck tends strongly to follow those people who work hard.